Okay, let's continue on with our discussion about steady state error. Remember, this is a different aspect that we have to look at when we're considering control systems, especially follower type controllers, where we are trying to keep the system at a particular value over a period of time. In some cases, we're not necessarily concerned about the transient response, how fast it gets to that point, but we're more interested in can it reach that point and stay on that point, or can it follow a path that we're giving it as an input? And so this is steady state error, and we looked at the general case, and then we looked at some specific cases, and now we're in the last lecture we boiled it down to this particular case where we're looking at freezing up again. Okay, where we looked at this particular case where we were identifying the system type as the number of free integrators, the number of S's in the denominator, and we call those free integrators, and the number of free integrators defines the type. And with that definition, we can create this nice little table in here that helps us in many cases because it gives us a good overview of what is happening. And we have our specific inputs in here, our step, our ramp, and our parabola. And then we have our types over here. And type 0 has no free integrators, type 1 has one free integrator, type 2 has two free integrators. And we saw that there were three different classifications. Some cases had infinite error, some cases had zero error, and then the remainder had non-zero constant error. And so in many cases we can just look at the system and say, oh, that's going to have zero error, or oh, that's going to have infinite error. And so it helps us to save a lot of time and effort in many cases. The only cases we really have to work on are the non-zero cases. So let's go ahead and do an example here and see how this all might play out. So let's imagine we've got a system in here defined by this transfer function, s plus 8 divided by s plus 7 over s plus 9. And with this transfer function, we'd like to find out, what kind of response we're going to get, steady state error we're going to get with this type of system. Well, we can look at this and just immediately say, well, it's a type 0. And so if it's a type 0, and because it is a type 0, we can say that for a step input, we're going to have a constant steady state error. With a ramp, it's going to be infinite, and a parabola, it's going to be infinite also. And so already 2 of the 3 cases we can just identify just by looking at the system. So the only case we really need to look at is the step input. And so the way we're going to do this is we're going to calculate a Kp, and this is not a gain, this is a constant, a position constant is how they're referring to it. It's a little bit confusing. I wish they wouldn't have used K's, but they did, and so that's what we have to live with. And so we come back here to our definitions, and our Kp is the limit of, as s goes to 0, of g of s. And so we've got the limit of, as s goes to 0, of g of s. And so now in this particular case, that's going to be the limit as s goes to 0 of 1000 s plus 8 over s plus 7 s plus 9. Okay, and of course this is the limit of s goes to 0. These drop out, and what we end up with is 1000 times 8 divided by 7 times 9. And we work that out, and it comes out to be 127 is our Kp. Now, we take our Kp back into this equation, and we end up with the steady state error for that. So the error at infinity, let me try that again. Error at infinity is equal to 1 over 1 plus kp, which is going to be 1 over 1 plus 127, and you work that out, and it ends up being 0.0078. So our error at infinity would be 0.0078. And so that would be, we would now know all three cases. We know the error at the step, the error at the ramp, or error at the parabola. Now, as far as the design concern, what we would do if we needed a zero steady-state error for the ramp, we would put a integral controller on this, a PI controller, and that would add a free integrator to the system and bring it one level, bring it to a type 2 or a type 1, and then we would have a steady-state error at a ramp. It would follow it, but it would be a little bit lag behind, just a little bit, and so that would give us a zero steady-state error for the step also. So anyway, let's see if we can verify these numbers with MATLAB. So I've gone into Simulink here and created just a couple of loops. I've got a step input here. Let's get my mouse going. I've got a step input into a closed loop transfer function, or a closed loop system with our transfer function in there. That's the same transfer function. And I've got a ramp input in here, and I put the same transfer function in here, which represents the system that we had. And so if we run this, we should get some output here, and we can look at the graphs, and this is the graph for the step input. It looks pretty good. If we zoom in here, let me see if I can zoom this. We do see we get a little error in here, and actually if you look at the value of our input, which is 1, and the value of our signal or our output, and subtract the two and get the error, it is right on the mark, 0.008, 0.0078, whatever. It does validate that our system our calculations were correct. Now the velocity is a little bit harder to interpret because it looks like it's following pretty well. But if you look at the difference here, where the time is small and then the time gets greater, you can see that down here at the time small, the two lines are virtually the same, and but as we progress along here, the lines start diverging. Okay, and we get the yellow line and then the blue line separately. And so, given enough time, these would separate by an infinite value. So that is a validation of our calculations, that these are diverging very slowly, but they are diverging. Okay, so that's the first type of problem you could expect to find on this homework.